Hello and welcome to this presentation. Today I'm going to present distributed Max-SINR speech enhancement with Ad-Hoc microphone arrays. This work has originally been presented in ICAST 2017 New Orleans. The problem of interest in this work is that the eigenspace approaches have not been adopted to fully distributed array processing. And these fully distributed array processing are aimed to work on Ad-Hoc microphone arrays which have unknown and dynamically changing geometries. The state-of-the-art distribute the global eigenproblem to local subarrays and solve small-size eigenproblems. However, there are restrictions to these methods. First of all, they are only efficient when the size of the subarrays are sufficiently large. Second, they don't work on cyclic networks. Third, they are sensitive to communication errors that are packet losses between local fusion centers. Therefore, we are proposing to break the eigenspace enhancement into iterative node-based or age-based operations. Therefore, contributions are twofold. First of all, we are employing the eigenspace in a fully distributed apparatus. Secondly, this method supports both synchronous and asynchronous iterates and is resilient to packet losses. The signal model here is simply addition of the vector of interference plus noise component to the target speech signal that has undergone the acoustic transfer function. We can write it simply as x plus v, in which x is the vector of desired components of the received signal over the nodes of the array. Then we can apply a filter with complex weight h to the received signal y, and by doing so we will obtain the output of the filter as z. Different criterion can be applied to h, one of which can be h that maximizes the signal to interference plus noise ratio, so we can write the optimization problem of max h of the ratio of the power of the filtered desired signal, H Hermitian phi xh, or the power of the filtered noise, H Hermitian phi vh. Equivalently, the Max-SINR filter can be obtained from the constraint optimization problem, in which the output or filtered desired signal power is maximized subject to the constraint that the output or residual noise power is 1. This solution is known to be principal eigenvector of the Hermitian definite generalized eigenvalue problem, which can be written in the form of phi xh equal to gamma phi vh, in which phi x and phi v are the complex power spectral densities of the desired and interference plus noise signals respectively. Then h is the eigenvector and gamma is the eigenvalue of this system. Assuming that the noise CPST is positive definite or invertible, then the solution would be equal to the principal eigenvector of the matrix phi v inverse phi x. We can denote this by Q1. Q1 can be computed in a distributed way using, for example, algorithms based on the power method. It should be noted that any distributed weighted averaging approach, such as Gaussian algorithm, can directly use the knowledge in Q1 to filter the received signal. However, in this work, another optimization problem is used to implement the Max-SINR filter. And by doing so, we facilitate a fully distributed implementation. Here, we find the weights that minimize a negative of H Hermitian phi yh, which is the filtered version of the received signal, and add to it some regularization term, which is required to make the problem convex, subject to the fact that H Hermitian Q1 is 1. Then, the CPST of the received signal can be estimated by the sample covariant matrix, so we do it by averaging over L past time frames. This centralized optimization problem can be solved in a distributed way. However, we need to decouple the node variables. To do so, we introduce some local variables called Zm at each node m. Then the optimization problem becomes the minimization of the negative of the summation over all nodes in the array and the average over L past time frames of the square or absolute value of Zm plus some regularization factors. Then subject to H Hermitian Q1 equal to 1 and also subject to the fact that summation of Zm over all nodes would be equal to m H Hermitian y. This optimization problem can be written in a more simplified way by introducing some matrices and vectors such that the lowercase omega m concatenates all of the output values Zm's at node m until the past L time frames, and then concatenated with the value of the filter weight at these nodes Hm. The matrix Qm is just contained of some regularization factors on this diagonal. The vector B being just a constant vector, and a matrix Am which includes the information about the received signal at node m by m for the current and the L previous time frames, and also the element of the eigenvector Q1m at node m. By doing so, we can rewrite the primal problem as a quadratic problem such that we minimize the summation over all nodes of omega m Hermitian Qm omega subject to a linear constraint, which is summation over all nodes of am omega m minus b equal to 0. Therefore, we have the primal problem in a fully distributed way. And to solve this problem in an efficient way, we just calculate the dual problem. So we minimize over the dual variable mu of summation over all nodes of mu Hermitian omega m mu minus 2 real component of b Hermitian mu. Here, the capital omega and omega m are defined as a mapping from am and qm to the new domain. This optimization problem can be solved using message padding methods for a tree-structured topology. They would be very fast converging, but they also need the knowledge of a tree, and the tree should be there for a while. But for arbitrary graphs with loops in them, the problem can be solved using methods such as ADMM or PDMM or etc. To show it for PDMM, we introduce local variables to the optimization problem, mu m at node m. Then for edge, for an edge that is connecting the node m to n, mu m should be equal to mu n. Now we have the PDMM update equations, and they are simply calculating at each iteration. We can calculate mu m, the primal dual, and the new nm, the dual variables for the h and m. And then at another iteration, we can update, and then we will reach the convergence after a while. A toy example is beneficial to study the proposed algorithm. Here we simulate a 5 in 5 in 3 meter room with 150 millimeter reverberation time using the image method. We simulate a situation in which 3 speakers, competitive speakers, from TSP-HP's database are available. A sampling frequency of 8 kHz is used with time frames of 64 microseconds with 50% overlapping Hanning windows. Then we simulate a teleconference application at the 3 speakers are sitting around the table, and then on the table we have 9 microphones distributed randomly. First thing to study would be the norm of residuals for the primal dual variable mu. So at node m we calculate after iteration k, and then k plus 1, and then forward. We calculate mu-m's, and then we calculated how they converge to the final value, so that we see the norm of the residuals of them over all nodes in the array, and then we can see that after a few hundred iterations, this norm of residuals drop down to something like 10 to the power of minus 8, which would be beneficial. After calculating as accurate as required these primal dual variables, then we can map them back to the primal variables omega, which contains the desired information, which would be the filter weights, and better than that, we would have the output filtered at each node. Convergence of the dual and even the primal variables in the distributed algorithm is not the ultimate goal of the speech enhancement. Therefore, we need to take into account some perceptual and intelligibility measures. In this slide, you can see the average output PESC measures for a distributed algorithm that's presented in this paper with the line blue. And we see that this solution converges fastly after 100 transmissions to the centralized solution of the Max-SINR filter. We can also look into how each nodes behave in this distributed system. So here we have dashed lines showing how the PESC improvement for each of the nodes would be. For the nodes that is closer to the desired signal, we expect the PESC improvement to be lower than the nodes that are further away. And we see that almost for most of the nodes, after 100 transmissions, all of the curves of the PESC improvements from the distributed methods reach to their final centralized solution. PESC is only one of the measures that we are interested in speech enhancement. Here at this slide, we look into the STOI measure, and we see how the distributed solution results in an output STOI that is converging to the result of a centralized algorithm. And we see that actually a STOI reaches to the proximity of some value close to 1 after 75, 80 iterations. I would end this presentation by some concluding remarks. First of all, we have presented a fully distributed Max-SINR beamformer in this work. We have seen that the convergence of the dual parameters after a few transmissions per node is sufficient to reach an acceptable level of quality with respect to PESC, STOI, and the like. We also have done some generalization and extension to the work that has presented in this presentation. We have generalized to distributed implementation of the Hermitian definite generalizing a value problem, so that we blindly find Q1 vector. And also we have generalized to distributed implementation of a class of variable span beamformers that can form MVDR beamformer, LCMV, signal distortion weighted, multi-channel Wiener filter, and the like. Thank you for your attention.